So these lectures are posted in the playlist on YouTube. This one will be posted maybe by 6 or 7 o'clock this evening, just so you know. Last week, we began our discussion of limits, and we saw two graphs like this. Now, the definition of a limit, remember, was that the limit of a function is some y value if, as the x values approach a given number, the y values also approach some other number. So we had a function like this. The numbers might be a little different, but we would mark off a point like 3, 4. And here, the limit as x approached 3 of our function was 4, because we could approach 3 from the left side. Well, we can approach 3 from the left side, and on the left of 3, these y values approach 4. But also, the other way we could approach 3 from the right side, the y values also approached 4. And because on both sides of 3, well, because in every way we could approach 3, the y values approached 4, we would say the limit of our function as x approaches 3 is 4. And we had another example where we put a hole in the graph and put that point somewhere else. And here, what would the limit be? Well, we still have these two ways of approaching 3, left and right. On the left of 3, the y values approach 4. And on the right of 3, the y values also approached 4. So in this second case, we had that the limit as x approached 3 of our function is also 4. The limit is 4, even though f of 3 doesn't equal 4. F of 3 is up here, it equals 6. But the limit cares only about what happens close to 3. Any questions about those two? These are reviews of the end of last Thursday's class. Let's look at another example. This one won't be a review. This will be a new example. Let's take this curve. Let's make it look like this. Let's put a hole there. Let's say 3 again. And let's have it look like this. So this function, well, it's defined in 2 pieces. We have this piece over here and then this piece up here. This hole is, let's say that's at 4. Let's say this is at 6, because we've been using those numbers. And the question is still going to be, what can we say about the limit as x approaches 3? That's the only x value marked off. Well, again, we have 2 ways to approach 3. I'm going to use the colors where they. We have the left side of 3, we have the right side of 3. And in these 2 examples, what the function did on both sides of 3 was the same. Well, and in the definition of limit, we said if for any way you approach 3, you get the same y value, that's the limit. What happens here? Well, let's look at the left of 3 first. What does this function do on the left of 3? Well, it approaches this open dot at y equals 4. So on the left of 3, the limit would be 4. So if we get on the right of 3 that the limit is also 4, then the limit is 4. But what happens here on the right of 3? On the right of 3, what does the function do? Well, the function's up here on the right of 3. And on the right of 3, the function approaches 6. And when that happens, well, let's go back to the definition of the limit from Friday. If all x values of f of x approach L as the values of x approach A, then we say the limit is that L value. So if all values approach a number as x approaches 3, well, we have two different numbers, 6 and 4, as x approaches 3, because we have multiple ways of approaching 3. When that happens, the limit will not exist. The limit as x approaches 3, let's say here. Here, the limit as x approaches 3 of f of x does not exist. Of course, you could write it as d and e if you want. Any questions about this one? Now, this example illustrates, well, it illustrates two things. One, it illustrates that it might be convenient to be able to describe, well, actually, all of these examples illustrate it might be convenient to describe what happens on each side of 3 separately. So we'll use this example to motivate this definition. So this will be kind of an informal definition using that example. So we're going to here describe what happens on the left and on the right using new notation. So in the previous example, we say, well, I'll just say in the previous example, on, let's do the right first, because I like writing positive before negative. On the right of 3, the limit is 6. So we'll say on the right of 3, not the limit as x approaches 3, we'll say limit as x approaches 3 with a positive superscript to mean on the right of 3. So right here, if we have a positive superscript on our limit notation, we're looking only at the positive side of 3. We're looking only at the right of 3. And in this example, on the right of 3, the limit did exist, and it was 6, because on the right of 3, this function approaches y value of 6. So we have a definition for the limit on the right. We also have a corresponding definition for the limit on the left of 3. Instead of a positive sign, we use a negative sign as the superscript. And in that previous example, on the left of 3, the y values approached 4. So the limit on the left of 3 was 4. So we have here, this limit doesn't exist because we had differing numbers resulting from the various ways we could approach 3. But here, the limit on the right and the limit on the left for that function will exist. Any questions about this definition? Now, in these first two examples, we could have also asked about the limits on the right and left. In both cases, the limit on the right and the limit on the left of 3 would both be 4, for reasonings similar to that one. But these 3 examples, together with that definition, suggest we have a larger theorem. So in these first 2 cases, the limit on the left of 3 and the limit on the right of 3 were both 4, and the limit existed. But over here, the limit on the right and the limit on the left differ, and the limit didn't exist. And that holds in general. So let's call that a theorem. Here. I'll just say limit as x approaches a of f of x does exist and equals the number L if and only if the limit as x approaches a on the right equals the limit as x approaches a on the left, and they both equal that same number. So the limit exists and is L exactly when the limits on both sides are that same number. And the previous example and the two recollections from last week illustrate that result. So if we want to show a limit exists, one way we can do that is by looking at both sides and getting the same number. If we want to show a limit doesn't exist, well, one way we can do that is by looking at both sides and showing we get a different number. Any questions about that theorem? So limits satisfy many nice algebraic properties, and they are contained in a document that I posted the other day. We'll talk about that in a moment, but before we get there, I'd like to look at two more examples. A horizontal line and a diagonal line, slope one going through the origin. So let's take this line, let's put it at, I don't know, 5, I guess that's a number. So here we have the line y equals 5. What is the limit? Maybe I should have used 4 since I used 4 in the previous exam. I guess I already wrote 5. Let's take a look at the limit as x approaches 3. Well, using this theorem, we'll look at both sides of 3. On the left of 3, the y values approach this point. The y values approach 5. On the right of 3, the y values also approach 5. So here, the limit as x approaches 3 by that theorem, technically by the definition we used, so here, the limit as x approaches 3 is 5, because on both sides of 3, the y values approach 5. Any questions about that? Okay. Now, this conclusion statement may be a little, it may not be obvious what is illustrated here algebraically with the way I wrote this conclusion statement, because f of x here is always 5. So what happens if we just replace f of x with 5? Well, then it would say, you know, f of x is always 5. So here it says the limit as x approaches 3 of 5 is 5. As x goes to 3, how does 5 change? Another way of saying it. As x approaches 3, 5 doesn't change. In fact, 5 is not a function of x. So the limit as x approaches 3 of just 5 is 5. And this result generalizes for any horizontal line. Now, I could have written this as f of x equals negative 5. I could have written it as f of x equals pi. But the more general result is that this holds for any constant. Am I going to call it a, let's not call it a theorem. Let's just say this generalizes for any constant. How does it generalize? Well, the limit as x approaches, well, let's not write the x approaches yet. The limit of y, I think I used c. Yeah, I used c in the picture I posted. The limit of c as x approaches what? Well, we can generalize the y value to any constant. But notice if I moved this 3 anywhere, we would have the same left and right side argument. So as x approaches any value in here, the limit would be 5 because of the theorem looking at both sides. Standard letter is A. So the limit as x approaches 3 of a constant is a constant, and the limit as x approaches any number of a constant is a constant. This is, well, it's a theorem, but I consolidated it in a PDF of algebraic limit laws. This is the first one in that list. So maybe I'll say this general for any constant c. I'll say define c. A is defined as in the definition. So right here, we have an algebraic result which can be shown using a generalization of that graph. Any questions about that first result? Well, first algebraic result. And one way of looking at this without even looking at the graph is by asking, well, how does C change as x approaches A? Well, C, in fact, doesn't change as x approaches A. And because of that, the limit would be C. Let's look at one more. Let's look at the line y equals x. Example. Let's take the line y equals x, so slope 1 going through the origin, x equals x. Let's pick the point 3. 3 will go through, or y equals x goes through 3, 3 in this case. Let's make this line shorter. So again, we're going to ask, what is the limit as x approaches 3? Well, on the left of 3, the y values approach 3. On the right of 3, the y values also approach 3. So the limit as x approaches 3 of this function is 3. Any questions about that before we generalize it? Now, this function here, f of x equals x, well, we can replace f of x with x because they're equal. So this graph is actually telling us as x approaches 3, the limit of x is 3. And this also generalizes because the ordered pair on this line, f of x equals x, is always going to be x value and the same x value on the y-axis. So 3, 3, 2, 2, negative 5, negative 5, and so on. So this also generalizes to the limit as x approaches any x value, and we could have moved this 3 anywhere. How would the y values change? Well, it would go through the point 2, 2, 4, 4, and so on. So on both sides, the limit would be that same x value. Limit as x approaches some number of x is that number from that graph. Any questions about that one? So that result there is our second algebraic limit law. Now it's an algebraic result here. The limit as x approaches a of x is a. One way of saying that, how does x change, or so how does x change as x approaches a? Well, as x approaches a, x approaches a from a curve like this. Any questions about that? Now, there are 5 other algebraic limit laws. I'm not going to write them all down here because the PDF is posted. So if you would like, I'm going to refer to this document just posted. It was also emailed to you. So you can take a moment and open that while I erase the board. So the first two limit laws are illustrated by those last two examples. The next four tell us about what happens in the limit as we add, multiply, and divide functions. So limit law 3, limit as x approaches a of f plus g, two functions. Well, the law says that we can do them one piece at a time. Maybe I will write some of these. So just to illustrate the third one, the limit of f plus g as x approaches a. Well, we could do that by taking the limit of f and then adding the limit of g. So if we have two things added together and we want to take their limit, we can do them one piece at a time by doing two limits. And that also holds for subtraction. If you have limit of something minus something else, you can do them one piece at a time. This also holds true for a product, rule 5, and a quotient, rule 6, provided the quotient exists. But rule 4, I'll illustrate. Rule 4 says if you want the limit of some constant times your function. This is a very important rule. We're going to use this and its consequences probably every week. Yeah, every week. Well, except week 1. The limit of a constant times a function, we can do that by pulling the constant out and then just taking the limit. So c times the limit in question. So if you have a constant in front of some function, you can take that constant out and then take the limit. Rule 7 says if you have something like x squared, you can deal with the x's and then you can just square the result, similar to rules 3, 5, and 6. But let's look at an example where we use these results. It's much easier to see what's going on with results when we actually use them. So let's look at this example. Now, these limit computations do require some practice. There's going to be a question on your first test. It'll almost definitely be number 1 that says, find the limits. And it'll be, I don't know, 15, 20 points, something like that. Just like number 1 on the worksheet and number 1 on the homework. Find the limit. Limit as x approaches 3 of what? X squared minus 4x plus 3. Now let's make it so it doesn't affect. Yeah, let's leave it. Some of you might have already written it, so I'm not going to make you use this. Limit as x approaches 3. So this example, we will illustrate the algebraic limit laws, and then we will see what they actually tell us about this example. So I'm going to title this example illustrating algebraic limit laws. So what do we have here? We have the limit of this function. Well, we could graph this. We could complete the square, graph it. It would be a parabola, with y-intercept, not y-intercept, with a, go through the point, 2, I don't know, -5 or something, 2, -1 maybe. Doesn't matter. Well, it could matter if you want to graph this, but graphing a parabola like this is kind of a chore with completing the square. So what we can do instead is use the algebraic limit laws, and we're not going to have to make reference to a graph. Now, what if I gave you a degree 5 that you couldn't graph yet? Well, then you would need to use the algebraic limit law. So what do we have here? We have the limit of some polynomial, but in particular, we have the limit of something plus something plus something. So we have the limit of 3 things added together. Rule, what was that? Rule 3, I think. Rule 3 tells us when we have things added together, we can do them one piece at a time. So equals by rule 3, so I'll write this like this, equals by rule 3, what? The limit as x approaches 3 of the first thing, plus, plus with a negative sign, so minus the limit as x approaches 3 of the second thing, plus limit as x approaches 3 of the third thing. So by rule 3, we split our limit into 3 other limits that we have to compute. Any questions about applying rule 3? Okay, so what can we do next? Well, we have 3 limits to consider. Let's look at them one piece at a time. Let's start with the first one. This is first. Limit as x approaches 3 of x squared. What do we have here? We have a function squared. Do we have any limit laws that tell us how to deal with a function squared? Well, rule 7 says the limit of a function squared is the limit of the function all squared. So by rule 7, with n equal to 2, I'm going to write this equal sign a little lower. By rule 7, we're going to use 3 rules here, so we're going to have 3 Roman numerals stacked there. By rule 7, with n equals 2, the first piece, we can compute that limit by pushing the limit inside the square, like that. Any questions about that first piece? We still haven't taken its limit. All we did was push the limit inside the square using rule 7. How about the next one? Well, we have a negative sign first. Limit as x approaches 3 of 4x. Well, do we have anything for 4 times a function? Well, yes, rule 4 with constant equals 4 says we can take that 4 outside of the limit. So by rule 4, in the second piece, we can pull the 4 out of the limit. We're left with the limit without the 4. So the limit as x approaches 3 of x. You can write the multiplication dot if you want there. So by rule 4, we can pull that constant out. Any questions about that step with the second part? How about the third part? Well, we have the limit as x approaches 3 of 3. Do we have a rule for that anywhere? Well, yes, we do. Rule 1 says the limit as x approaches 3 of a constant is that constant. Limit as x approaches 3 of 3 is 3. How does x change? Or sorry, how does 3 change as x approaches 3? Well, 3 doesn't change. So by rule 1, that third limit is 3. While we still haven't computed this limit, we still have a couple limits to take. Let's do the first one. Inside the square, limit as x approaches 3 of x. Well, rule 2 tells us that that limit as x approaches 3 is 3. So by rule 2, the first limit is 3, and that's inside the square. The next one, we have that 4 there, but let's not worry about that yet. Negative 4. Limit as x approaches 3 of x, well, that's the same limit. That limit is 3 by rule 2. So we have negative 4 times 3, and that last thing is a 3. That we already took its limit. So we have these numbers to add, 9 minus 12 plus 3. So that limit is 0. So right here, we illustrated what? Rules 1, 2, 3, 4, and 7. Any questions about that one before we make this observation. So observe what applying these limit rules actually allowed us to do. Applying the limit rules turned it into substituting x equals 3. What would happen if you substitute x equals 3 in that original limit? Observe, substitute substituting x equals 3 into the original limit gives, what does substituting 3 into the limit into the original limit give? Well, it gives us the limit as x approaches 3 of x squared minus 4x plus 3 equals, substitute x equals 3. You get 3 squared minus 4 times 3 plus 3, which is the same as this last, second to last line, equals 0. So these algebraic limit laws tell us that when we can make a substitution into an algebraic function, we can find the limit by making that substitution. Any questions about that? Okay, so let's do another. Let's do, so we didn't illustrate rules 5 and 6. Their illustrations are similar. Let's just do this example. Example, find this limit. Limit as x approaches 5 of x plus 2 times the square root of x squared minus 3. Maybe I should make it simplify. Now let's leave it like that, that's fine. Find this limit. Well, you can, if you want, apply the algebraic limit law. So I'll just say one solution uses algebraic limit laws directly. Which ones? Well, first we have something times something else. You'd use the product rule, the product law number 5, and then you'd use rule 3 to break the sum. Then you'd use rule, the first 2, and then you'd use the 7. So one solution uses those 5 rules directly, and you can go through the details similarly to how we did the first example if you want. But I'm going to use this observation. Another solution does technically use the algebraic limit laws, but it uses them indirectly because we saw that using them when substitution worked was equivalent to doing a direct substitution. And in this case, what would the limit be? X plus 2 root x squared minus 3. Well, let x equal 5, and what do you get? 5 plus 2 is 7. 5 squared is 25. 25 minus 3 is 22. 22 and a square root is the square root of 22. So any questions about that example? Okay. So let's consolidate these observations. We haven't done the limit of a fraction, a rational function or anything like that yet. But let's summarize the limit laws in a more usable way, and then take some more limits. Let's call this a theorem. Theorem. I like how I wrote it in my notes, so I'm going to follow that. For general f of x and g of x, upon direct substitution limit, which limit? This limit as x approaches a of the quotient. So this is a general result. We'll talk more about these quotients in a moment. The limit of that quotient takes one of the following forms. And this is going to be a list of 4 things after this. This theorem follows from the limit laws in this observation. I'm going to write this here so that I would normally write the first 4 and then write this line, but I don't want you to squeeze this in after I write the list of 4 here. I'm going to use the number sign, pound sign, to stand for a non-zero number. Here, that'll stand for non-zero. So upon direct substitution, this limit can take one of these forms. 4 forms. First 2 are technically about the same. First, you can get a 0 in the numerator and a non-zero in the denominator. So 0 will stand for 0. The pound sign will stand for a non-zero number, whole or positive or negative, whole or not whole. So upon direct substitution, the limit can take 0 over a number. After these, I'm going to write a sentence or 2. We could also get a number, non-zero number, over a non-zero number. Upon direct substitution, the quotient can take that form. We can also get a 0 over a 0. So you can get a 0 in the top and a 0 in the bottom. And fourth, what else can we get? Well, we can get a number in the top, but a 0 in the bottom. So now the first few examples we did technically are satisfied here because you could let the denominator just equal 1. And that would fall under number 2 or number 1, I guess. But what happens, so the limit takes one of these forms upon direct substitution. What happens, or what is the actual limit? Well, in these first 2 cases, 0 over a number, 0 over a non-zero is 0. Number over number is a number. So here, this, let's say, reduced fraction is the limit in question. So if you do a substitution and you get a 0 over a number or a number over a number, that is the actual limit. And why is it the limit? Well, it uses the algebraic limit laws. Technically, it also uses a result we're going to cover tomorrow, but we'll see that tomorrow. So if you do a substitution and you get a 0 or a number, then that will give you the limit. What about case 3, 0 over 0? Well, 0 over 0 is not a number, but we'll see in the limit it can behave like, well, it can behave actually like any number. So I'll just say here, now this case 3 in many ways is the most interesting of all these cases. So we will look at a few examples, but for this theorem, I'll just say here, we'll do some algebra until the 0 over 0 goes away, and we are left in case 1 or 2. So when we do some examples, we'll see more about what we mean by do algebra. We'll also see more about what we mean by until the 0 over 0 goes away. And we're going to do several examples. Most of them will involve case 3. But if you do a substitution and get a 0 over a 0, we have to do algebra. If you do a substitution, you get 0 over a number over a number, that's your limit. Now what about this last case? You get a number in top and a 0 in the bottom. We'll look at this case later today. So I'll just say for this theorem here, I'll just say here there's an asymptote. And I'll put in parentheses. Now the actual description of case 4 is like 3 or 4 sentences, but so I'll just say here there's an asymptote, and I'll say later today. So here we have a general result. Let's look at actually applying this result. Well, any questions about anything that's written before we use this theorem? Okay, so let's look at these few examples. Let's start with 2 examples. One thing the algebraic limit laws and a result we're going to see tomorrow tell us is that direct substitution may work. And if it does work, that's very convenient because if you want the limit, that's all you need to do. Let's look at this example. Limit as x approaches, let's do -3 of x minus 3 over x plus 3. And let's do this example. Limit as x approaches, let's do this example I wrote here. 3 of this fraction, 4x squared minus 3x plus 2 over x minus 7. So let's use this theorem. We have a fraction. Try a direct substitution, and which form it takes upon substitution will tell us some useful information. What do we get upon direct substitution here? Well, let x equal, this limit is as x goes to -3, so let's let x equal -3. So that's what we mean by direct substitution. Let x equal -3. On the top, you get -3 minus 3. On the bottom, you get -3 plus 3. -3 minus 3. Oh, I didn't do the example I want. Did I really not write that right? Okay. Well, let's do 3 examples. You get -6 over 0, case 4. I'll just say vertical. Vertical asymptote. Again, that'll be later today. I wrote the wrong question. It was not a good mistake I made. The one I wanted to ask was case 1, not case 4. And the first example should be case 1. That was not a good mistake I just made. Okay, let's do this, this example instead. What happens if you do a direct substitution here? As x approaches -3, you get -3 plus 3 on top. You get -3 minus 3 on the bottom. On the top, -3 plus 3 is 0. On the bottom, -3 minus 3 is -6. 0 over -6, well, that puts us in case 1. The reduced fraction is the limit. 0 divided into -6 is 0. So that limit is 0. In case 1, this fraction always reduces to 0. So that's part of why I said reduced fraction. And notice because of this, these equal signs are all correct. Any questions about what should have been the first example? Let's look at the second one. Again, this theorem tells us direct substitution tells us nice information. What does it tell us about this one? Well, do a direct substitution here. You get 4 times 3 squared, 4 times 9, minus 3 times 3, plus 2, all over 3 minus 7. What does this equal? Well, on the top, you get what? 36 minus 3 times 3 is 9, plus 2. In the bottom, you get -4. 36 plus 2, 38. 38 minus 9, 29. 29 divided into -4, -29/4. Puts us in case 2. That fraction is reduced, so this is the limit, -29/4. And again, both of these, you could have applied the algebraic limit laws directly. But these functions are much larger than our first example where we illustrated them. So illustrating them would take a good amount of time. So I like to use this consolidated result. Any questions about that one? So those first 2 examples illustrate cases 1 and 2. Let's look at another. We're actually going to look right now at 3 examples which illustrate case 3. Let's start with this one. Case 3, here, do algebra, what does that mean? Until 0 over 0 goes away, what does that mean? Well, let's look at an example. X squared, make sure I write it right. Limit as x approaches 2 of x squared minus x minus 2 over x squared plus x minus 6. Well, I told you we're in case 3 before starting this example, but why are we in case 3? Well, again, let's do a direct substitution. A direct substitution can be useful. Now, in these first 2 examples, once we interpreted our direct substitution, we were done. So maybe that'll happen here. What happens upon direct substitution here? You get 4 minus 2 over 4 plus 2 minus 6. 4 minus 2 minus 2 is 0. 4 plus 2 minus 6 is 0. So right here, we wind up in the 0 over 0 case. Because of that, 0 over 0 isn't a number, so I'm just going to get rid of that first equal sign. But being in the 0 over 0 case tells us that we have some work to do. We need to do algebra, something is going to cancel, and then we may be left in case 1 or 2. What kind of algebra can we do? Well, what kind of algebra can we do? Well, we have 2 degree 2 polynomials, maybe they'll factor. They do factor. The top factors, numbers which multiply to -2, add to -1. -2 plus 1 is -1. the top factors like that. Does the bottom factor? Well, it does factor also. The bottom numbers which add to 1, multiply -6, -2, and +3 do that. So the top and the bottom of this fraction both factor. Does that help us? Well, it does help us. We haven't taken a limit yet, so notice we still have equals a limit. Now, once we take the limit, we no longer need the limit. But we haven't taken a limit. All we did was factor. The top factored and the bottom factored, and what happened? Well, when we factored, we wound up with the same piece on the top as we have in the bottom. The top has an x minus 2, the bottom has an x minus 2, meaning this fraction reduces. How does it reduce? It reduces into this fraction, x plus 1 over x plus 3. And again, we still had not taken a limit, but we did reduce the fraction by factor and canceling. Any questions about the 2 steps we did? Okay, so now what can we do? We did some algebra, something canceled. Are we left in case 1 and 2? Meaning, can we do a direct substitution? Well, what happens upon direct substitution here? X equals 2, you get 2 plus 1, x equals 2, you get 2 plus 3. So we have 3 on top, 5 on the bottom. We're in case 2. So the limit is 3 divided by 3/5. Any questions about this one? So in the description of that theorem, it said do algebra until the 0 over 0 goes away. That is a very informal, imprecise statement in math. But I think it's illustrative, well, in all 3 examples we're about to do, but in this one as well, because notice, if you did do a substitution in this middle step, you would get a 0 times a 3 and a 0 times a 5 here, and the things causing the zeros happen to cancel. Now, is that consistent with something I had said earlier? I said, when writing that statement of the theorem, I said 0 over 0 is not a number. But here it looks like we're saying 0 over 0 equals 1. Well, I will tell you, 0 divided by 0 is not 1. So the question would be, why does this canceling actually work? You know, it looks like we're saying 0 over 0 equals 1. But we're not, because that's not true. So while I'm writing the next question, think about, why does that canceling actually work? Why can we do that? We're not saying 0 over 0 equals 1. So in this step over here, when we did this canceling, we didn't say 0 divided by 0 equals 1, because this limit doesn't care what happens when x equals 2. When x equals 2, this fraction is 0 over 0. But the limit cares what happens close to 2. In the definition of the limit, we never said it matters what happens at x equals 2. What matters is what happens close to 2. And close to 2, this fraction, x minus 2 over x minus 2, does always simplify to 1, because it's always a number over itself. So it doesn't matter what happens when x equals 2 in this simplification. We can, using that previous theorem, interpret what happens, or use what happens at x equals 2 to interpret the limit. But we can't ever say 0 divided by 0 is 1. This limit cares only what happens close to 2. Any questions about that? Okay, let's look at this next example. Limit as x approaches -4, root x plus 13 minus 3 over x plus 4. Again, let's try a direct substitution and see if that gives us a number. If it doesn't give us a number, let's see what it does give us. Let x equal -4, you get root 9 on top, minus 3. You get -4 plus 4. Root 9 minus 3 is 0. -4 plus 4 is 0. So again, we're in case 3. We have a 0 over 0 case. So we're going to have to do some algebra. Well, what algebra can we do? Well, algebra with square roots is far more inconvenient than algebra without square roots. So one thing we can do, one thing we can do is change what this function looks like by multiplying by a convenient 1. We're going to write 1 as a fraction. We're going to write 1 as a convenient fraction, which will allow for a nice simplification of our square root. Which one will we take? Well, if we multiply the numerator by that, we will see a convenient substitution. But we can't change the function. We can only multiply by 1. So we have to multiply by 1. This 1 will cause the numerator to simplify conveniently. Now, why does that happen? Well, this isn't a random quantity. Notice we got this. Notice this quantity in the numerator differs just in that sign. Now, why does that simplify nicely? Well, on the side, we will recall an algebra result. I'll write it like this to parallel this example. So this limit computation will take a couple lines. So this recall in your notes, if you're taking notes, should be separated a little from the rest of the work. Recall a plus b times a minus b simplifies into a squared minus b squared. Recall the difference of squares result, which says a squared minus b squared is a plus b times a minus b. So in this numerator, we have something which takes this left-hand form. A minus b times a plus b. This minus 3 times this plus 3. And in that case, the product simplifies to the first thing squared minus the second thing squared. The first thing squared, square root of x plus 13 squared, is x plus 13. Minus the second thing squared, the second thing is a 3. 3 squared is 9. So our numerator, using that difference of squares observation, simplifies a little. Notice in the numerator, the square root went away because we squared the two pieces. Any questions about the numerator? Now, what about the denominator? Well, you could, if you want, I would always recommend against it. You could distribute everything, but we'll see in a moment why leaving it undistributed is more useful. So in the denominator, I'm just going to leave it as the first thing times the second thing. So the denominator, I didn't distribute at all. The numerator, we did simplify using that difference of squares. Any questions about that first step? So notice we haven't taken a limit yet. We just did some algebra. In this case, we multiplied by a convenient 1. But what can we do? Well, in the numerator, we have 13 minus 9. We can combine those. This equals the limit. Still as x approaches negative, where 13 minus 9 is 4. So in the numerator, we have an x plus 4. In the denominator, we won't do anything yet. So all we did here, add the 13 and the negative 9. And doing that, notice, turned it into a fraction in which there's an x plus 4 on top and an x plus 4 on the bottom. This fraction reduces. X plus 4 divided by x plus 4 is itself, or it says itself, is 1 at all values except x equals negative 4. So it simplifies because the limit doesn't care what happens at negative 4. How does it simplify? Well, that reduces to 1, so we're left with a 1 on top and an x plus 13 under a square root plus a 3. And now we did algebra. What was causing our 0 over 0 to appear canceled in that step. Now we hope we can do a substitution. What happens when you substitute? You get a 1 on top. You get a root 9 plus 3. So you get 1 over 3 plus 3, 1/6. Any questions about that one? Well, now one of the reasons, well, the main reason I didn't distribute this x plus 4 is because the goal in these 0 over 0s is to arrive at an equation where, in this case, an x plus 4 showed up in the top and the bottom. So here, the x plus 4 was already there. Any questions about this one? Okay, let's look at one more of these case 3 examples. And let's look at the algebra we would have to do here. When I do math, I always like to use unlined paper. Because I find the lines very much in the way, especially when I have large fractions. Let's take this large fraction. 1 over x plus 1 minus a half over x minus 1. And we want the limit of that as x approaches 1. Well, again, we have a limit. What happens upon direct substitution? Let x equal 1. You get a half minus a half over 1 minus 1. You let x equal 1. We again have a 0 over 0. This tells us we need to do some algebra.
When we do work for these problems, do we have to show the step where we determine that it would become 0 over 0?
You don't. I always like to, so you notice in the last 2 examples I erased where I got 0 over 0. You don't have to show that. But it is a good habit to get into substituting. And seeing if substituting works, because it's very common on a calculus test, either this first test or the final, to have a list, find these 3 limits, or find these 4 limits, or however many, and one of them is a direct substitution. So if you had one like this, let's see, let's make it factor. So if you had an example like this, if you didn't jump straight into a direct substitution, these two pieces do factor. X minus 2, x plus 4 on top, x plus 2, x plus 3 on the bottom. And if you did that, well, you would wind up, well, first of all, nothing would cancel, but notice in this step, if you substitute, you get 0 over some number, which equals 0. So it may be that you can factor and then do a substitution and nothing would cancel, but it would probably save time if you just looked at a substitution right at the beginning. And so today we're just covering some algebraic limit results. Tomorrow, we're going to talk about limits of trig functions and some others, and we're going to get a similar result. But in those, in particular, the direct substitution at the beginning, in those, using a direct substitution at the beginning could save a lot of hassle. So I would recommend getting into the habit, because it's, you know, I put one on a test I think it was in the fall, and direct substitution gave the answer in 5 seconds, but there was another simplification you could have done, which would eventually get you the same answer, but that simplification would take like 5 minutes. So I would always recommend, you know, you don't have to write it down. And the question was, do we have to write it down? So you don't have to write it down, but I would recommend getting into the habit of doing a direct substitution. So what is this limit? Well, we got a 0 over 0, so we're going to need to do some algebra. What algebra can we do here? Well, the numerator we can add together as one fraction. The denominator in the numerator would be 2 times x plus 1. The first piece, we need to put a 2 there to get that common denominator of 2x plus 1. In the second piece, well, we have a negative, but we need, in order to get the denominator to be 2x plus 1, we need an x plus 1. So we'll put one of them on top as well. So our numerator, if we combine those fractions, combines like that. The denominator, we don't need to do anything with. Notice in the denominator, we already have an x minus 1. We already have what is causing our 0 to appear there. Any questions about that first simplification? Whenever I have a 3-tiered fraction, I like to be sure I'm drawing the overall fraction bar much larger than the rest. Helps keep me organized. So what can we do with this? Well, let's do 2 things. We have this top fraction divided by x minus 1. Well, no, let's do that second. How does this overall numerator simplify? 2 minus x minus 1. 2 minus 1 is 1. So the overall numerator simplifies to 1 minus x. Not the numerator of the numerator, I should say. So the top of that fraction, we get 1 minus x divided by that. We haven't done anything with that. But we can also take care of the overall denominator, because remember, division is the same as multiplying by a reciprocal. You know, dividing by 7 is the same as multiplying by 1/7. So dividing by x minus 1 is the same as multiplying by 1 over x minus 1. We can simplify that fraction a little further. We get rid of the 1 tier by multiplying the numerator by 1 over x minus 1. Any questions about getting here? Now, we need to eventually cancel out what's causing our 0 over 0 to appear. We're not technically there yet, even though when you let x equal 1, that gives you a 0, and this gives you a 0. Because 1 minus x and x minus 1 are not the same thing. You can only divide two things and get 1 when they're exactly the same. These two things aren't the same. This one has a negative x, this has a positive x. This has a positive 1, this has a negative 1. But they are similar. They do differ by a negative. So in that numerator, we can factor out a negative. The numerator factors into negative x minus 1. And we didn't do anything with the denominator. So 2x plus 1 times x minus 1. And now that we took that negative out, an x minus 1 appears in the numerator and the denominator. They cancel. The limit is now the limit as x approaches 1. If this cancels with this, in the numerator we're left with a negative 1. In the denominator we're left with a 2 and an x plus 1. We did all that algebra. We hope a substitution works. It does, because you get negative 1 over 2 times 2, which is negative 1/4. Any questions about this one? So we had 3 different types of simplifications in that case 3 case of our main theorem. So any questions about any of those first few limits we did? Okay, so let's debating if I want to do case 4 first or talk about asymptotes first. Well, let's erase the board and then decide. Before directly looking at case 4 of that theorem, let's recall 2 graphs and let's use them to interpret what we mean by infinity. Infinity is not a number. Infinity is a symbol we use in math to mean a quantity gets larger than all numbers. What does that mean? Well, let's look at this curve. Let's look at f of x equals 1 over x, and let's look at f of x equals 1 over x squared. 2 of our graphs from last week. I'm going to write something here about that curve. I'll draw the other one over here. So we have f of x equals 1 over x and f of x equals 1 over x squared. What happens in this first one and the second one? What happens in this first one as x approaches 0? Well, first notice that first curve is not defined at x equals 0. At x equals 0, you do a substitution, you get 1 over 0. It's not a number. But what happens as x approaches 0? Well, two ways we can approach 0. We can approach 0 on the left of 0, in which case the curve is going down like this. Or we can approach 0 from the right of 0, in which case the curve approaches that piece up there, well, in which case the curve goes up. So notice, let's look at the right of 0 first. On the right of 0, what would our limit be? Well, this curve keeps going up. Keeps going up. It keeps getting larger. So if you said the limit was some number, this curve would eventually go higher than that number. When it gets higher than all finite numbers, we say that that limit is infinity. I'm going to write, I believe, 4 limits here. Well, the limit as x approaches 0 on the right of 0 of this curve, 1 over x, is the limit. The curve gets larger than all finite numbers. In that case, we say the limit is infinity, and in this case, we say positive because it's positive. Is that visible on your screens, that limit I just wrote? It is. Okay, I'm looking at my computer screen. It's a little less visible than I wanted it to be. But on the right of 0, the limit is positive infinity because it gets larger than all finite numbers. What happens on the left of 0? Well, a similar thing, but it goes in the negative direction. If you said that that limit was, this negative number down here, negative a billion, well, this curve goes lower than that number you chose, negative a billion. So in that case, the limit as x approaches 0, we only looked at the left of 0 in blue, of 1 over x is negative infinity. It gets smaller than all numbers. In that case, we say the limit is negative infinity. Any questions about those 2 limits? So we're using those, we're really using them to define positive and negative infinity. But any questions about those? So, like I said, I was going to write 4 things. I'm actually going to write only 3 things. When this happens, well, before when this happens, let's observe this other graph. Again, let's look at the left and right of 0. Over here. Here we have 1 over x squared. Let's look at the left and right of 0. On the right of 0, this goes up. Limit would be positive infinity. With positive infinity, we don't write the positive sign. I wrote it in the first one just for illustration purposes. But just like with numbers, if there's no positive sign, we assume it's the positive. So on the right of 0, this curve over here went to positive infinity. On the left of 0, the curve also goes to positive infinity. Now, in these cases, we would say, in these cases, we would say that this curve or the other curve has a vertical asymptote at x equals 0. So here, f of x has a vertical asymptote. Maybe I'll say has vertical asymptote x equals 0. And I could have said it has a vertical asymptote at x equals 0. I'll just say the vertical asymptote is the line x equals 0. And why is that? Well, let's also say it over here. Here, f of x has vertical asymptote x equals 0 as well. Now, why does that happen? Well, the technical definition for a vertical asymptote is that one of these is going to be satisfied. On one side of 0, or the other side of 0, or both sides of 0, the function goes up to infinity or goes down to negative infinity. And notice how this parallels the fourth result from our limit theorem. The fourth result said that if you do a substitution and you get a number over a 0, then the curve will have a vertical asymptote. And the vertical asymptotes could look like one of four things. They could look like this, where on the one side you have positive infinity, on the other side you have negative infinity. They could look like this, where they both go up. The other two they could look like are, if you flip this over, they both go down to negative infinity, or if these are flipped around. I won't draw those. We'll look at that more algebraically. But in both of these curves, if you had to take, if I said find the limit as x approaches 0 of 1 over x, upon a direct substitution, you would wind yourself up in case 4. You'd get a 1 over a 0, or a 1 over a 0. And let's write that as a remark. Well, let's erase that, and then I'll write it as a remark so I don't squeeze it into the side over there. And let's look at a couple computations. Remark. Case I don't know, start this sentence. A case 4 limit, or case 4 is from previous theorem. Looks like, so it gives you a vertical asymptote, but it looks like one of the following. So it could look like those first two. I guess I will draw all four of them. It could look like that, like the first curve. It could look like this second curve. It could look like that flipped around. Maybe I'll draw some arrows. Or it could look like this one over here flipped around. Meaning, if you do a substitution and you get a number over a 0, then it tells you there's vertical asymptote, but you can actually algebraically figure out more, because you can figure out what happens on both sides of what's causing the 0. In this first case, on the right, you have a positive infinity. On the left, you have a negative infinity. In this case, on the right and the left, you have a positive infinity. In this case, on the right, it goes to negative infinity, on the left to positive infinity, and here on the right and the left, they both go to negative infinity. So let's look at two examples. Let's look at two examples of this. So let's first look at this example, and let's look at both sides of 3. So notice at x equals 3 in this, sorry, that should be plus 3 on top. What am I doing? Writing the wrong one. That was an easy fix. So here, notice when x equals 3, you get a number over a 0. That tells you we have a vertical asymptote. So right here, we're going to look at both sides of 3 to figure out which one of these it looks like. Meaning, on the one side of 3, we're going to have a positive or negative infinity. On the other side of 3, we're going to have a positive or a negative infinity here. We just need to figure out what happens on both sides. And conveniently, we can use algebra to figure that out. How can we do that? Well, infinity is not a number, meaning infinity plus something doesn't give you a number. It'll give you another infinity. But it does satisfy the standard multiplication sign rules, meaning an infinity times a positive 7 is a positive infinity. Infinity times a negative 7 is a negative infinity. And similarly for negative infinity, meaning right here upon direct substitution on each side of 3, we know it's going to be either an infinity or a negative infinity. If we want to figure out which one, then all we have to do is worry about the signs on both sides of 3. How can we do that? Well, there are a couple ways you could do it. You could do a direct substitution on the right of 3 and the left of 3. I won't do that because these, I put a larger problem on the worksheet for that reason. But what we can do here is factor this. At the top, we don't have to factor, it's already factored. The bottom, you can pull out an x. And you're left with x times x minus 3. And now, this fraction is written as 3 things multiplied and divided together. X plus 3, x, and x minus 3. And they're all multiplied and divided. So, again, substituting 3 here tells us that this limit will be an infinity. We need to figure out positive or negative infinity. And we can do that by looking at the signs of these 3 pieces. This notation isn't, well, it's kind of standard. You see it in some textbooks. Our textbook does something a little different. So this isn't a negative sign in front of us. Instead, this is going to be a large fraction bar. And what are we going to put in this fraction? Well, we have 1 thing in the numerator, 2 things in the denominator. What we're going to do is look at both sides of 3. Well, we're going to look at, in this case, the right of 3, down here, the left of 3. What do we mean, the right of 3? Well, we mean x values over here. What happens on the right of 3? Bearing in mind, all we really need to concern ourselves with is the sign. Because we know it's going to be an infinity, we need the sign. On the right of 3, what happens in this numerator? Well, a number larger than 3 plus 3 is a positive number. On the right of 3, what happens to x? Well, it's still a positive number. On the right of 3, what happens to x minus 3? So on the right of 3, you take numbers larger than 3, subtract 3, well, you still have a positive number. So in that first one, we have 3 positives multiplied and an infinity, which gives us a positive infinity. Any questions about that first limit? So these are just looking at what happens to each of these pieces. What is the sign of each of these pieces on the right of 3? So let's do the same thing with the left of 3. Again, this will factor. 3 over x times x minus 3. And again, you let x equals 3, number over 0. So we know it's going to be n infinity. We have to interpret the sign. On the left of 3, what numbers are on the left of 3? Well, here's 3. Numbers on the left of 3 are numbers over here, less than 3. Take a number close to 3, but on the left of 3, add 3, you still have a positive number. Add number, or take numbers close to 3 on the left of 3, substitute them for x, you again have a positive number. Take numbers close to 3, but on the left of 3, subtract 3, what happens? Well, if you take a number on the left of 3, subtract 3, you wind up on the other side of 0, which gives you a negative. Positive times negative gives us a negative infinity. Any questions about either of those two? So this tells us that that the curve x plus 3 over x squared minus 3x looks like, it looks like something like this. Vertical asymptote at x equals 3, but on the right, it goes up to infinity. On the left, it goes down to negative infinity.
I have a question.
Yes.
I'm confused with it. When are you substituting like the limits? Are you substituting the x, or like you substitute x equals -3 and x plus 3, or?
Well, here we're looking at x equals positive 3.
Okay.
So yeah, this remember when the sign is after, we're just looking at 3, but this means we're looking, the limit is looking at the right of 3, and this one's looking at the left of 3, but it's still looking at positive 3.
Oh, okay. Thank you.
Following that question, let's look at another example where we have more signs. My second example was going to be one with a few more signs. So let's look at this one. For this one, I'm just going to look at one of the limits. Limit as x approaches, let's do -2, and let's do it from the right. So here we have the limit as x approaches -2 from the right of what? Let's cube that one, I guess. Let's cube it. X. Okay, so let's take this limit. So this one, we have only the right side of -2. You could ask, well, I could ask also the left side of -2, but the argument would be similar. Well, let's do the right side first. So if you try to substitution x equals -2, you would get a number on top, you get a 0 on the bottom. You get a 0 on the bottom because of that x plus 2 term. So that tells you immediately, on the one side of -2, you'll have an infinity, positive, negative. On the other side, you'll have an infinity, positive, negative. So we know our answer is going to be an infinity. We need the sign. So which part of the number line are we looking at here? Well, we're looking at -2. And we're looking at the right of -2. Sometimes in these, especially with the negatives, I like marking off 0 just, and I'm not good with right or left, so sometimes I like marking off the 0. So here we're looking at -2, but we're looking only at the right. we need the sign of the infinity, so we're going to need the signs of these 5 pieces. As x approaches -2 from the right, take numbers on the right of -2, add 3. Well, that's going to push you to the other side of 0, making a positive. Take numbers on the right of -2, close to -2, subtract 4. Well, that's still going to be negative. It becomes more negative. So we have a negative. And notice we have a negative cubed. Negative cubed is still negative. So you could handle this by writing like a cubed and then interpret it. I'm just going to leave it as a negative like that and take care of the cube by observing negative cubed is a negative. Any questions about the numerator? Okay, now the denominator, numbers close to -2 on the right of -2, add 1. Well, that's not going to push you on the other side of 0. So you have a negative, but we're squaring it. Negative squared is positive. Maybe I'll write that as a side. Negative squared is positive for that piece. Yeah, okay, negative squared is positive. How about this next piece, x plus 2 all cubed? Well, take numbers to the right of -2, add 2. That's going to push you to the other side of 0, which makes a positive. Positive cubed is positive. Take numbers on the right of -2, add 4. Well, it's going to push you even more positive. So here we have one negative sign, and you have negative times positive times positive times positive times positive. It gives you a negative infinity. Any questions about that one? So it's worth observing a couple things here. One, notice this quantity squared, we had a negative squared. If we had a positive squared, it would still be positive. So if you have one of these and the exponent is even, you don't even have to think about the substitution, because when the exponent is even, it will always give you a positive. That's one thing worth observing. Another thing worth observing here, we won't do this example. Well, I won't do this example, but it's worth checking later today. If I ask the limit as x approaches 2 from the left, limit as x approaches 2 from the left, so I'll just say here, limit x approaches -2 from the left of that function, I will tell you it's positive infinity. And it's definitely worth checking with the signs later today. But any questions about that? Now, this tells us some information about vertical asymptotes. Let's more formally define vertical asymptotes. Can't find where I wrote vertical asymptotes in my notes. This is definition. Let's define vertical and horizontal asymptotes. So from case 4 of our theorem, a vertical asymptote will occur when the top is not 0 and the bottom is 0. So I'll just say, the curve f of x, I should write it like this. P of x over q of x, they're both polynomials, has vertical asymptotes when the denominator equals 0. Following case 3, but also following those first two curves we discussed, y equals 1 over x, y equals 1 over x squared. So let's look at an example. Find my notes on these. Oh, they're the next page. Huh. What's that? Okay, so let's find the vertical asymptotes of a curve. This one. We're going to see this curve in a few moments too. Well, this rational function, I should say. We're not going to actually look at the curve. So let's first find vertical asymptotes of this function. Well, by the definition over here, it has vertical asymptotes when the denominator equals 0. So let's find where the denominator equals 0. X squared minus 4x equals 0. Solve this for x. Well, we can factor an x out of this. Both of these terms on the left have an x. X times 5x minus 4 equals 0. So x equals 0 or 5x minus 4 equals 0. So you get x equals 0. X equals 4/5. A vertical asymptote is a vertical line written as x equals a number. So I'll just say we solve this, but solving it directly gives us our vertical asymptotes. So set the bottom equal to 0. Doing that gives us our vertical asymptotes. Any questions about that one? Okay, so let's now talk a little about horizontal asymptotes. But to do that, we need a little more information on limits. So let's do that. First, what is a horizontal asymptote? Well, let's again go back to our curve y equals 1 over x, and you could do the same with 1 over x squared. 1 over x looks like this. Let's call this example. F of x equals 1 over x. Now I will tell you this has a vertical asymptote. Well, it has a vertical asymptote. It also has a horizontal asymptote. Why? Now what is a horizontal asymptote? Well, a horizontal asymptote occurs when the function approaches a horizontal line. So how can a function approach a horizontal line? Well, it can look like this. as x keeps getting large, this curve keeps approaching the horizontal line y equals 0. Here, in that previous statement, I said as x gets large. As x keeps going in the positive direction, this curve keeps going down but stays positive. It keeps going down and stays positive. It will approach height 0. Here, the limit as x goes to infinity. Limit as x goes to infinity. We're going in the positive direction on the x-axis. Limit as x goes to infinity is 0. Stays positive, but it keeps going down. That limit is 0. Any questions about that first limit that I just wrote there? The curve 1 over x is very useful for understanding infinity. In this context, but also in the vertical asymptote context. From that, we know that the curve has a horizontal asymptote. We could have also looked in the negative direction. In the negative direction, the limit is also 0. It's staying negative, but it's still approaching the horizontal line y equals 0. And in the negative direction, so the limit as x goes to negative infinity. We're looking at x values that keep getting more negative. Limit as x goes to negative infinity of 1 over x is also 0. From this, we can say that this curve has horizontal asymptote y equals 0. A horizontal asymptote is a horizontal line written as y equals a number. From that curve, well, from those limit observations, we could say it has horizontal asymptote. Now, before more formally defining a horizontal asymptote, let's look at another curve. And that one was 1 over x. Let's look at one that we don't know anything about except its graph. Let's say it looks like this. Now let's say it looks like this. Here's a curve, it's some function. Let's say that's at 2. Let's say that's at -3. I'm going to draw out these lines y equals 2 and y equals -3. So we'll ask 2 questions here. What is the limit as x approaches infinity of this function? And what is the limit as x approaches negative infinity of this function? Well, what happens as x approaches infinity? As x keeps getting larger, this curve follows that arrow, which is approaching the line y equals 2. So it approaches the height 2, it approaches y value of 2. So the limit as x goes to infinity of that curve is 2. What about the limit as x approaches negative infinity? Well, we look at the negative side. As x keeps getting more and more negative, the curve goes down to -3. So that limit is -3. And, well, any questions about these 2 limits? So that first example over there, 1 over x, had only the one horizontal asymptote, but this example here has two horizontal asymptotes. It has one in the positive direction and one in the negative direction. So in the, I'll just say here, this is still in this example. Here, f of x has horizontal asymptotes. Y equals 2 and y equals -3. Notice we could arrive at a horizontal asymptote in the positive direction or by looking at the negative direction. Any questions about that? Now, we still haven't formally defined horizontal asymptotes, so let's do that now. Definition. Notice we could have a horizontal asymptote in the positive direction or the negative direction, and they could be different. Or as in the example I just erased, they could be the same. So f of x, well, no, I'll say it like this. If the limit as x approaches infinity of f of x equals some number, let's call it L1, or the limit as x approaches negative infinity of f of x equals L2, then we say f of x has horizontal asymptotes. By horizontal lines, y equals L1 and y equals L2. And L1 and L2 may be the same. They may be different. So to find vertical asymptotes, we looked where the denominator was 0. To find horizontal asymptotes, we're going to have to look at two limits. Limit as x goes to infinity and limit as x goes to negative infinity. So let's do that. Well, we don't have time to draw all of it. Yeah, we don't have time to do any of it. The next example is going to be find the horizontal asymptotes of that same curve, 2x squared minus 3 over whatever the one we found the vertical ones for. But we'll start with that tomorrow. We'll have time tomorrow to do that. But definitely for today, do practice some of those limits like number 1 in the worksheet. Now, you can't do all of them from number 1 on the worksheet. I'll tell you which ones you can't do because we're going to cover them. You can't do C. Oh, you can only do A or B. So for tomorrow, it's a good idea to practice problems 1A and 1B on the worksheet, and also problem 2. I guess you could find the horizontal asymptotes for 3 as well, or the vertical ones for 3 if you want. But limits like 1A and 1B are pretty important, especially the algebra for one of them like 1B. Any questions? Okay, so well, tomorrow we'll finish the topics for this week. Later today, I will send you an email with a little more information on the test. But I hope you enjoy your Wednesday, and I will see you tomorrow.